Today in this class I will solve a problem in the flat slab. Okay. First let us consider the problem. Design the interior panel of a large single story warehouse flat slab roof with drop panel of size 6 meter by 6 meter is supported by a column of size 500 by 500 mm. The height of the column is 5 meter. Take a live load of 3 kN per m squared and the weight of the finishing including the waterproof treatment as 2.5 kN per m squared. Use M25 grade concrete and Fe 4 and 5 grade steel. Assume the mild environment. So the given flat slab has to be designed with drop panel for a size of 6 meter by 6 meter. The column size is given as a square of 500 mm. The height of the column is 5 meter. That need not to be used anywhere in this problem. Live load can be considered as 3 kN per m squared. Then roof finish, they are given the waterproof treatment, therefore definitely that will be a roof. That finishing load as 2.5 kN per m squared. The grade of concrete is given as M25, grade of steel is given as Fe 4 and 5. Assume to use the mild environment, therefore this has to be considered while assuming the clear cover for the main reinforcement. In the first step, we have to arrive the thickness of the slab and dimensions. So thickness can be arrived based on the stiffness criteria. Any design has to be satisfied both strength as well as stiffness criteria. Here, since it is an interior panel, it will be continuous all around. Therefore, I have to use the basic value corresponding to the continuous slab. That value is 40. That is provided in the class 24.1, page 39 of IS 456. Since we are using a HYSD bar, that value has to be multiplied with term 0.8. So finally we got 32 as a L by D ratio. Our aim is to find the effective depth. So therefore keep the effective depth on one side. The simplify, keep the other terms on the other side. So span by 32, where span is 6 meter. So 6 by 32 will give 187.5 mm. This is the effective depth required as per the stiffness criteria. But as per the class 31.2.1, page 53, we have to provide a minimum thickness of 125 mm for the flat slab. But our required dimension itself greater than the 125 mm, so we are safe here. Now I am assuming a clear cover of 20 mm and will let the diameter of the bar used as 12 mm. Based on this, I will arrive the overall depth required, capital D is effective depth plus clear cover. Clear cover assumed as 20 mm, then diameter of the bar by 2, that is diameter of the bar assumed as 12 mm. So finally I will get the overall depth required as 213.5 mm. And round off to the nearest value. I will adapt a overall depth of the slab as 215 mm. 215 mm. Here in the flat slab we have a slab as well as a drop. We have a drop. Now I have assumed the dimension for the slab. To identify the depth of the slab and the depth of the drop, I will subscribe the letter S for the slab, subscribe the letter D for the drop. Now I will arrive the effective depth provided based on the overall depth. 215 minus 20 minus 12 by 2 will give 189 mm. Now we have a effective depth and overall depth. Next we have to find the dimension for the drop. Minimum depth of the drop panel is 1/4 of the depth of the slab. Depth of the slab assumed as 215, 1/4 of that value is 53.75. I am assuming that value as 60. By adding these two values, I got the overall depth of the drop as 275 mm. That is greater than 1.25 times the depth of the slab. So the assumed dimension satisfied the conditions. Next, let me refer the clause 31.2.2. As per that clause, the drop dimension should not be less than 1/3 of the panel dimension. Our panel size is 6 meter by 6 meter, therefore 6 by 3 will give 2000 mm. This is the minimum size required for the drop as per the code. Before assuming this dimension, let me calculate the width of the column strip, width of the middle strip. Based on that, I can assume this value. As per the clause 31.1.1, the width of the column strip should be 0.25 L2. 0.25 L2 width of the column strip. This value, சொல்லுங்க. Clause 31.1.1. As per the clause 31.1, the column strip dimension is 0.25 L2 on the either side of the center line of the column, but it should not be greater than 0.25 L1. Okay, that means the least of these two values has to be used for the width of the column strip. Since in this problem we have a panel size of 6 meter by 6 meter, therefore L2 and L1 are equal. If suppose in the examination, if they asked to design a panel size for 7 meter by 5 meter, means you have to calculate 0.25 into 7, 0.25 into 5. Least among these two values can be used for the width of the column strip. So width of the column strip is 1500 mm on each side of the center line of the column. That should be greater than or equal to the drop dimension. The minimum drop dimension required is 2000. If we provide the 1500 mm on either side of the center line of the column, total width will be 3000. The 3000 will be greater than 2000. To avoid the confusions while substituting the values in the problem, I will keep the width of the column strip equal to width of the drop. The minimum requirement is 2000. I am providing 3000. So we are on safer side. So I am providing a drop panel of size 3 meter by 3 meter. Then width of the column strip as 3 meter. Then what is the width of the middle strip of that? Let me draw the diagram for this plan. Okay, this is a 500 by 500 mm column. This is the other column. So I am drawing the plan view for the 4 of the columns. So the center to center dimension from here to here, here to here, here to here again, here to here as 6 meter. That is the panel size. Okay. For column strip, 1.5 meter on the either side of the center line of the column. So here again 1.5 meter. Here also, in this case also I have 1.5 on the either side. Here also I have 1.5 on either side of this center line. So final width I got here as 1.5 on either side of the column. Total width as 3 meter. So here also I have a 3 meter. Here also 3 meter. Here also 3 meter. But now I am, if you consider the middle strip, which is bounded by column strip on all the sides, at the middle, this dimension is again 3 meter by 3 meter, because total width is 6 meter. You have to detect 1.5 for column strip on the top, 1.5 at the bottom. So remaining will be the 3 meter in this direction. Similarly on the other direction also 3 meter. So finally I have kept all the values are equal. Width of the column strip, width of the middle strip, width of the drop panel, everything I have kept as 3 meter. So we should not have any confusion in later on stage while substituting these values in the equations. This is for the simplification purpose. Next, step 2. In this step, we can calculate the loads acting on the flat slab. We have arrived the depth of the slab as 215 mm. So first I will calculate the self weight of the slab as 0.2515 into density of the concrete. Density of the R.C.C is 25 kN per m square. I multiply this, I got the value of 5.375 kN per m square. This is the load due to the slab. In addition to that, I have to add the height of the drop. The drop is the additional thickness provided over the column. The additional thickness I have provided here as a 60 mm. See here. I have provided as a 60 mm. So I will add the weight of that portion. That's 60. I am converting here into meter. 0.06 into 25 will give the 1.5 kN per m square. This is the additional dead load due to the extra thickness at the drop location. Then live load given in the problem as 3 kN per m square. The finishing roof load as 2.5 kN per m square. By summing all these values, I got a total working load as 12.375 kN per m square. To make it as a factored one, I will multiply this by using the load factor 1.5. Finally, I got the value of 18.56 kN per m square. This is the total design load acting on the flat slab. Is 18.56 kN per m square. Okay, now step 2 is over. Let us start the step 3. That is for ultimate bending moment calculations. For that, you have to refer the class 31.4.2.2 on page number 55. Let me open that page number 55 for your reference. ISO files. The absolute sum of positive and average negative bending moments in each direction shall be taken as m0 is equal to WLN by 8. This is the absolute sum of positive and negative moments. The total, where m0 is total moment, where W is the design load on that area, which can be calculated by on the yield of L2 into Ln. Capital W is equal to small w, that is UDL load into span. Finally, if you multiply again one more L here, you will get the formula as like a simply supported beam WL squared by 8. Where Ln is the clear span extending from face to face of the columns. We have a two columns. From face to face of the column will give the Ln. if suppose if you provided a capital or column head in for your columns, means you have to measure from the face of the column head to the face of the column head in the but no case not less than 0.65 L1. Okay. Then L1 is the length of the span in the direction of M0. So this is the total bend. Here the panel size is 6 meter by 6 meter. I will calculate bending in only one direction. If the panel size is in rectangular 7 meter by 5 meter means you have to calculate for the longer direction, also calculate for the shorter direction. This M0, if you are using a longer direction means first you can keep that as a L1. The shorter direction you can keep that as a L1. This is the length of the span transfers to L1 can be called as a coming to another point. Here I have shown this bit of details. This square cannot be considered. L and L is the clear span extending from face to face of the column. Here the size of the column is 500 mm, that is 0.5 meter. This column to this column. Face to face column distance. We know that center to center distance is 6 meter. So we have to deduct half of the column size on the either side. So totally one column size I have deducted here. So obtained value is 5.5 meter. The condition is it should not be less than 0.65 L2. The 0.65 L1. 0.65 L1. 0.65 into here panel size is 6 or 3.9. It is greater than 5.5. So I can use the value as it is. Then 18.56 is the total load arrived in the step 2. Then 6 meter is the L2. Then 5.5 is the L1. So total load is design load is 612.48 km into LNL. Small LNL is 5.5 divided by 8. You can get the total absolute moment as 421.08 kNm. 421.08 kNm. This moment including positive and negative values. Next we have to distribute this moment to column strip as well as for the middle strip. As per the class 31.4.3.2 on page 55. So for interior span, the total design moment M0 shall be distributed in the following proportions. Negative design moment is 0.65 times M0, positive value is remaining value 0.35 times M0. So first I will divide the total moment into negative and positive. So total negative moment is 0.65 times M0, that value is 273.7 kNm. So if you deduct this value from the total moment, you can get the balance as 147.4 kN meter. That has to be assigned for as a total positive design moment. Now I have divided the total moment into negative moment and positive moment. Then I have to distribute this negative moment to column strip as well as middle strip. What is the total negative moment? 273.7 kNm. So the 273.7 can be divided into column strip as well as middle strip. For that I have to refer the class 31.5.5.1 page 57. 31.5.5.1 page 57. For the column strip, the interior strip, column strip shall be designed to resist 75% of the total negative moment. So 75% can be shared by column strip, The remaining 25% has to be given to the middle strip as per the code. So I am doing here 75% of this value as 205.3 that will be assigned to for column strip. The remaining value as 68.4 that is assigned to middle strip. Similarly, I have to distribute that positive moment to column strip as well as the middle strip. For that, I have to refer the class 31.5.5.3 on page 57. 31.5.5.3. Column strip, positive moment for each span. Column strip shall be designed to resist 60% of the total positive moment in the panel. So 60% will be shared by column strip. That means the remaining 40% has to be given to the middle strip. So the total positive moment 60% is 88.4 that is assigned to column strip. The balanced moment is 59 that is the 40% that is assigned to middle strip. So in this step I have calculated the absolute sum of moment of positive and negative values. Then I have split to positive and negative. Then positive and negative values again split to column strip and middle strip. Then step 3 is over. Next I have to check the thickness assumed are enough to resist the bending moment. We have provided used two thickness. One is thickness for the slab, another one is thickness for the drop. First I will check the thickness of the slab at the drops. The effective depth required D required equal to square root of mu by Ru max into B. This formula is arrived by equating that bending moment to the limiting moment of resistance. Where Ru max is the moment of resistance factor that depends upon the grade of concrete and the grade of steel. Here we are using the Fe 4 and 5 grade steel, therefore we have to use 0.138 into FCK. Here the grade of concrete is M25, so we have to substitute FCK value as 25. Here Mu, which value has to be? Now I am talking about the drops. Let me see the drop is located where in the plan view. This is the plan. This is the column. So around the column we have a drop for a dimension of 3 meter by 3 meters. So drop is located at the column strip. So I have to consider the moment in the column strip. That also negative moment because that is a higher value, that is 205.3. So for this moment I am calculating the effective depth required as 140.84 mm. Here I have used the B value as the width of the drop. I have assumed as 3 meter to avoid the confusion. So this is the effective depth required to resist this bending moment. But the provided effective depth is, the overall depth is 275. I am deducting the clear cover, then diameter of the first layer, then half of the diameter of the second layer. At the drop locations, we have a negative bending moment in the column strip at the top. We know that flat slab is designed as a two-way slab. The main reinforcement has to be provided in both the ways. So at the drop location I am providing the main reinforcement first layer, this will be the second layer. So I am considering the worst case as the second layer. That's why I have deducted minus 12, again minus 12 by 2. That is 237 mm. This is the provided one. Provided one is well ahead of the required one, hence okay. Next I will check the thickness required at the middle strip, that is the thickness of the slab. For that I have to consider the bending moment in the middle strip. The maximum value has to be considered, either negative or positive. Here the maximum value is 68.4 in the middle strip. So I will use the value of MU as 68.4. Here again RU max, we know that 0.138 into FCK. Here FCK is 25. Here B. What is the size of the middle strip? What is the size of the middle strip here? What is the size? 3 by 3. So again I have to substitute the B value as 3000, got the value as 81.29 mm. This value is much lesser than the provided effective depth of 189, hence OK. Therefore, depth provided is sufficient at the location of drop and slab. Then it will be designed as an under reinforced. Next step is reinforcement calculations. I have to calculate the area of steel at 4 locations. So we have positive value, negative value, we have column strip, we have middle strip. So I will start from the column strip. First I will calculate the area of steel required for the column strip. Then I will go with the negative bending moment. We know the formula to calculate the area of steel as 0.5 SCK by Fy 1 minus square root of 1 minus 4.6 MU by FCK being squared the whole into 3, where FCK is, that is, depends upon the grade of concrete. Here the grade of concrete is 25, I have substituted the value as 25. Fy is the yield strength of the steel, given in the problem as 4 and 5, so that also I have substituted. Then Mu, which moment I have to be used? I have 4 different values. Now we are talking about the negative bending moment in the column strip. So we have to use the corresponding moment value. This is the negative moment. This is the column strip. The corresponding value is 205.3. So I am using the 205.3 into 10 power 6 to make it as a Newton moment. Then FCK 25 B again. Column strip size is 3 meter by 3 meter. There is no confusion on that. Then effective depth at the drop, they are provided as 237. Already we have worked out here. That value is 237. I am using the same value of 237 here. Then again B as 3000, D as 237. Then simplifying by using a calculator, you can arrive the value of the AST required as 2552.558 mm square. Let us assume to use the 12 mm dia bars. And I will calculate the number of bars required, where n equal to total AST divided by area of the 1 bar. That will give the total number of bars required as 22.57. I will round off to the nearest value as 23. I will find the spacing by dividing the total width of the column strip by number of bars. We will give the spacing. The spacing required is 130.43 mm. Therefore, I am providing a 12 mm dia bar at 130 mm center to center in the column strip at the support as we are talking about negative bending moment. So this is a top steel. Okay. Then for positive bending moment, again the same formula, same substitutions. Only variation here is that we have to use the corresponding positive bending moment value for column strip. Let's again go to the moment table. Here, now we are talking about the column strip, talking about the positive bending moment. Therefore, the corresponding value is 88.4 kNm. So, I have to use the value of 88.4 kNm in that AST required equation. Again, there is a small change. Why I have changed the effective depth value here? Any guess? There is no. So we are talking about the positive bending moment in the column strip. Let me show in the plan view. We have a column strip. This is the column strip. We have a column strip. Negative values are at near the supports. Positive values at the midspan bottom. At the midspan of the column strip, we have only the thickness of the slab. There is no drop at that location. Therefore, we have to use the corresponding effective depth. The effective depth of the slab as already we have arrived as 189 mm. I have used that value in that equation. We should be very careful while using the effective depth values. So here we have two changes. One is bending moment, another one is effective depth. Then simplifying this equation, we can get the value of 1349.416 mm squared as the area of steel required. I have a doubt. Let me check this value with the minimum area of steel required. Minimum steel for the slab is 0.12% of the gross area, 0.12 by 100 into D. Here B is 3000 D. D should be a overall D. Overall D should be corresponding to this effective depth. That is 215. The AST required is minimum is 774. That the AST required is greater than the minimum. So we can comfortably use the AST required. Again I am using the 12 dia bars. Number of bars required equal to total AST divided by area of 1 bar will give the number of bars as 11.93. I will round off this to a 12. Then I will calculate the spacing required by total width divided by number of bars will give the spacing. This is spacing required as 250 mm. So I am assuming to use 12 dia bars at 240 mm center to center in the column strip as bottom steel. Now my calculation is over for column strip. I have calculated for positive bending moment and negative bending. Similarly, I have to do the same calculation for the middle strip. I will quickly go through this one. For middle strip, let me consider the negative bending moment first. You know the formula. In this formula, we got to substitute the appropriate values. The bending moment, then effective depth and the breadth. We know that the size of the middle strip is again 3 meter by 3 meter. Therefore, breadth B is 3000 again. Then at the middle strip we have only one thickness, that is the thickness of the slab. The corresponding effective depth is 189. So I used the value of 189. The moment I have to check with the moment table again for negative bending moment. Negative bending moment of the middle strip. Since see this is middle strip, this is negative bending moment again. The value is 68.4. The value is 68.4 kNm. I have to use this value. For positive, 59. So first I will calculate for 68.4, then 59. So 68.4 I have substituted here. So the AST required is 1054.181 mm squared. I am calculating the number of bars required as 9.14. Then I will round off this to the nearest value as 10. Then find the spacing by total width divided by number of bars is 300 mm. I am providing a 12 dia bars up to 250 mm center to center in the, I can make this correction, there's a middle strip. Middle strip at the support, because since it is a negative bending moment. Then coming to the positive bending moment, again same AST formula. I am using the corresponding bending moment as positive value at the middle strip as 59 kilonewton meter. Using the same value, the rest of the things are same. The value arrived as 888.14 mm squared. I am checking this value with the minimum AST. The minimum AST required is 774 mm squared. The AST required is again greater than the AST minimum. AST minimum. So I will calculate the number of bars required for the AST required. This is the total AST divided by area of 1 bar will give the number of bars You round up this value to 8. Then spacing required is 375 mm. I am providing 300 mm spacing as a bottom steel. As a bottom steel, because we are designing for the middle strip positive value. So we can convert this also into a middle strip. The overall, the maximum spacing should not exceed 2 times the slab thickness as per the code. This value will not exceed 2 times the slab thickness. Slab thickness is 215. 215 into 2, 430 mm. I have provided only 300 mm. So it is much less than the 430. So it is not exceed the limits. Again, the last step is check for shear. Check for shear is a very important step. Here we have provided the slab with the drop. So I have to check the shear, critical section for shear at 2 locations. One is from the face of the column, another one is from the edge of the drop. We have 2 possibilities. The column can be either punched through the drop location, and the column and the drop can punch the slab from the edge of the column. So see the code itself given these details. This is the slab with drop and column head. In our problem, we don't have a drop. We only have a column of 500 mm size. This diagram has to be altered like this without column head. So first I have to consider the critical section is at t/2 distance from the face of the column, since I don't have a column head. So this critical section will cut at the location of the drop. Therefore, the D should be DD, corresponding to the drop thickness. Then the second location is we have to check the critical section for shear from the edge of the drop. Edge of the drop is again D/2. This is to be considered all around the column. So this is the elevation view. I will show the plan view also. This critical section is again D/2. Here I have to use the D as corresponding to the slab, because punching is going to happen in the slab. Therefore I have to use the effective depth corresponding to the slab. Here the punching is going to happen at the drop too. Therefore I have to use the effective depth corresponding to the drop. Okay. So this is the plan view. I am showing the column size as 500 by 500. The critical section is DD/2 on the either side. So this is the critical section parts. See, this is also a square. What is the length of the one side of this critical section, critical plane is 500. 500 plus either side we have to add DD/2. So therefore I am adding what is 1 DD. Therefore 500 plus DD. The critical section for shear is checked at a distance of DD/2, that is 237/2 from face of the column, that is the all around the column. First I am calculating the perimeter of the critical section, that is B0. I have to add the length of these 4 sides of this critical section. The one side length is 500 plus DD, that is 500 plus DD is 237. So we have 4 sides. I have multiplied by using the 4. So I got the perimeter as 2948 mm. So perimeter has arrived. Next I have to calculate the ultimate shear force on these critical sections, which will be caused to develop a punching shear. For that, VU equal to, since it is an ultimate shear, I am using the ultimate load. the calculated in the second step as 18.56 kN per m square. Okay, I have to change this value kilonewton per meter square to kilonewton, means I have to multiply that with area. Then I will consider the area. Which area? I am considering only one column, which is an interior panel. The adjacent column to this one is 6 meter away from here, again 6 meter away from here, all the direction. The adjacent column is 6 meter away from here. So how much load will transfer to this column? The adjacent column is 6 meter away from here. So therefore half of the load, that is up to the 3 meter distance load, will be transferred to this. Similarly on all the sides. So the total load coming to this column as in one direction is 6 meter, other direction is again 6 meter. Therefore the total load is 6 by 6. So 18.56 into 6 by 6 will give the total load. But the resistance will be along the perimeter. Resistance will be along the perimeter. Therefore I have to calculate this area of this critical section portion. The total area that has to be divided with the total area, that is the unbalanced shear here, that will cause the punching. So the one side width is 500 plus 237, 737 mm. I am converting that into a meter, 0.73 on the one side of the critical section. We have a area 0.73 into 0.73 will give the area of the critical section. That has to be deducted from the total area to get the unbalanced force. So 18.56 into 6 squared minus 0.77 squared will give the ultimate shear, which will cause the punching. So that value is arrived at 658.08 kilonewton. Next, I have to calculate the nominal shear stress. Nominal means actual shear stress. To calculate the nominal shear stress, the formula is provided at class 31.6.2.1, page 57. Yes, 6, page 57. See, the nominal shear stress in the flat slab shall be taken as E by B naught into D. We used already calculated the V value. B naught is the periphery of the critical section, that is the perimeter. I already calculated that value. Again D is the effective depth. So I used this formula to calculate the nominal shear stress. So U by V naught into D. To make it clear, I have put U for ultimate shear force because it is multiplied with the load factor already. So U is 658.08 into 10 power 3 Newton divided by area. Area is shear perimeter, or that is the perimeter of the critical section, 2948 into effective depth 237 will give the nominal shear stress value as, after simplifying, we can get the value of 0.941 Newton per mm square. 0.941 Newton per mm square. Now we arrived at the actual shear stress. Next what we have to do. We have to compare this with the permissible shear stress. The permissible shear stress can be calculated according to the class 31.6.3, page 58. Page 58. The permissible shear stress without shear reinforcement is Ks into tau c, where Ks equal to 0.5 plus beta c, but it should not be greater than 1 in any case, where beta c being the ratio of the short side to long side of the column / capital. Here we don't have a column capital, therefore we have to calculate the ratio between short side to long side of the column. 500 by 500 again 1, 0.5 plus 1 is 1.5. The condition is it should not greater than 1. Therefore, we have to use the Ks value as 1. Tau c, we are using the limit state design. Therefore, tau c is 0.25 into root FCK, where FCK is the characteristic compressive strength of the concrete. For M25, it is 25. So, permissible CSS Ks into tau c, Ks is 0.5 plus beta c. In no case, it should not be greater than 1. Okay. Beta c is 0.5 by 0.5 equal to 1. Then substituting here, Ks is 1.5. But no case it should not be greater than 1. Therefore, I am using Ks equal to 1. Permissible shear stress as Ks into tau c is 0.25 into root FCK. FCK is 25. Arrived at the permissible shear stress value is 1.25 Newton per mm square. Greater than the nominal shear stress. So, we are safe in punching shear at the drop location. There is no need to provide reinforcement in the drop locations of shear. No reinforcement means we are not talking about the AST for bending. I am talking about the shear. Then coming to the critical section in the slab. Here I have clearly given the calculations. You can slowly go through these calculations. If the time permits, you can do this calculation in the examination. Because if the slab is safe at the drop location, means definitely it will be safe at the slab location. Because we have a critical section is calculated from the edge of the drop. Drop panel size itself 3 meter by 3 meter. So again adding the ds by 2 on the either side, we can get the one side length as 3000 plus 189 mm. So totally 3.189 mm. We can get the one side of the critical section. So since the shear perimeter is higher, automatically actual shear stress value will be reduced. See the calculation. See the calculation. Nominal shear stress is much reduced, 0.198. But the permissible shear stress will be again the same 1.25. It will be much greater than the actual value. Therefore, it is safe at the slab locations. Instead of doing these calculations and all, you can simply write this step. The shear strength at the critical section of ds by 2 from the drop also has to be checked. It will be safe because the drop size is very large. The shear force at this location will be lesser and also nominal shear stress will be considerably reduced.